Good? Okay, awesome. All right, so we'll finish up discussing the what you need to change in your execution engine. So unlike what we've been talking about so far, for this, I broke it, didn't I? Fine? Okay. For this discussion, we'll focus primarily on analytical queries, or OLAP queries, because for these types of workloads, this is where you actually generate a lot of intermediate results as you execute the query. So in a OLTP query, you usually probe an index, you grab a single tuple, and you spit that back to the application or client. In analytical queries is where you're actually doing sorting and hashing and other things where you have to generate a lot of intermediate results. So there has been some research done at Edinburgh on limiting the amount of writes you have to do for sort of traditional query processing algorithms, so in particular sorting and joins. And the way to sort of think about these new algorithms is that you essentially have a knob that the database system can adjust that will make a trade-off between the number of writes that you have to do when you process the query versus the performance boost you'll get. So as you do fewer writes, you actually get slower because you try to reduce the amount of materialization you have to do as you process the algorithms. But then the trade-off for that is you end up not wearing down the device as quickly. So I'll sort of go through at two high level, the two key algorithms that they present, and this is something you can consider when you build your database system. So the first is to do a sorting algorithm that's a hybrid or combination of two different algorithms that have different characteristics or write profiles and performance characteristics. So the way to sort of think about this is you say you have a single input sequence. You can choose to have some portion of it be run under a selection sort, which has a fewer number of writes but is slower. And then you can have a other portion of the input sequence run with the merge sort, which is faster but has more writes. And again, there's a trade-off that you make internally based on how many writes you're willing to incur and how quickly your storage device will burn out. So this is different than the hybrid sorting you see in something like the STL, which actually does one sorting algorithm from the beginning, which I think is quicksort, and then they use heap sort for the later sorted runs because that's much faster when things are already sorted. This is actually taking a single input sequence and actually running different algorithms on different portions of it. And in a similar vein, you can apply the same technique to do a hash join, where you can have some portion of the input sequence on the probe side actually be split into partitions and then materialize them into a hash table. And then other portions you don't want to materialize in a hash table at all, and you simply just iterate over them and probe the hash table built on the build side. And again, internally, the database system can make a decision about how many writes it's willing to incur and decide how much, where to tune this knob. So now the next thing we can talk about is extensions you can add to SQL to allow a database administrator to provide more information to the underlying database system to say where it actually wants to store data and how it wants to actually use MVM. So these don't actually exist in the standard yet, but these are just some proposals that people have put out there to say how a human can control what the database system actually does with data. So the first is that you can basically tell the data system to take a single table or materialized view and materialize it entirely in NVM. Right? So say you have a table that is accessed a lot or modified a lot in your workload, you can specify that you want to store this in NVM because that will be much faster than storing it out on an SSD. Similarly, you can also specify that you want to store the entire table in NVM, but maybe you want to provide a blacklist or exclusion list to tell the database system which columns you actually don't want to store in NVM at all. So you can sort of, if you have a column store system, you can say, store these columns on SSDs, store these columns on NVM. And again, there's certain performance characteristics or trade-offs you have to make when you make these types of decisions that the database system will be able to know now because you specified it in when you declared your tables. And so we think that this is actually a very open problem that is something that people should look into going forward. And it'll be interesting to see how this sort of standardizes over time. We suspect the way this is first going to happen is that all the different database vendors will provide initial instructions in their administrative tools that allow the DBAs to specify what's stored in NVM, what's not stored in NVM. And then eventually there'll be constructs in SQL that allow you to declare this information. And how long it takes before that actually ends up in the SQL standard remains to be seen. Note also too, the sort of two examples that I showed were all about telling the data system actually where to store data. None of this had to do with actually what algorithms the system would want to use and whether things should be in NVM or not. Right? This is all strictly for storage. Yes?
Why is it so critical to have this extension when you don't have an extension which says store on HDD versus store on SSD?
So I think in Oracle you can specify that some things are SSD versus HDD. Oh. Right? And actually I think this syntax here is derived from Oracle's system. We think it's important because, again, we're database people, we love SQL. It'd be nice if there was something in the standard that makes these things actually be portable. What's that? Sorry.
Okay, so it's an argument whether that would be nice or not. It could be the opposite.
So his statement is it's debatable whether that's nice or not. Yes, let's take that offline. Okay. Okay, the main takeaway I would say here is, though, again, I didn't show you, say, like, do a hash join with NVM. I didn't say, I'm not saying you want to specify those things, because that would sort of break the declarative nature of SQL. I'm just saying you can provide more information to tell the data system where to actually store stuff. Okay, so now if you have actually stuff stored in NVM, and the data system knows that it's in NVM, now we actually have to also consider how we modify our query optimizer to take this in consideration. So the first thing I'll say is that I'm not stating that you actually need to change the overarching architecture or search model of your optimizer, meaning whether you want a stratified search model or a unified search model, Volcano versus Starburst, that doesn't change. The only thing you actually now need to change is the cost model inside the system and how it decides whether one plan has a lower cost relative to another plan. And the key change that needs to happen here is that we need to be able to now no longer have to make the distinction that you would in a disk-based system, that there is a major difference between sequential access and random access. So in Postgres, for example, the way their cost model works is you define a bunch of constants relative to the cost of doing a random write to a single page or random read access to a single page. Right? And so and you declare constants to say the sequential access is much faster than random access. So in a new MVMware cost model, you don't have to make this distinction anymore because, as we showed before, the relative costs are negligible. But now you need to make a difference between the cost of doing reads and writes in your cost model to allow you to pick an optimal query plan. And so the high-level way to sort of think about this is in the context of sequential access and random access is in the traditional case where you would account for you would say that the cost of doing a sequential scan is the same versus it's a read or a write. Now we actually need to modify our cost model to modify it to say if you're doing an update to the database, the cost of doing a sequential read is distinct from doing a cost of a sequential write or a random write. And likewise, if you're doing a join, you no longer want to make a distinction between the reads and writes as you either do on the build side or the probe side. These are now essentially the same, right? And you no longer need to worry about doing a distinction between the random reads and random writes as well. So in the work done, I think, in Germany, they built a new cost model in Postgres that actually was NVM aware, and they ran this on the NVM emulator. And they want to compare the query plans that were generated by Postgres using the traditional Postgres model that's sort of based around the cost of page access on disk versus this new NVM aware one. And they're going to run the TPCH benchmark and see what the performance differences are for the query plans that they generate. And the overall average, the major finding of this is that when they use their NVMware cost model on NVM storage, on average, the Postgres was able to pick query plans that had a 50% improvement over performance over the disk-based cost model. And in the maximum case for one particular query, they got a 500% improvement, which actually is quite significant. It shows, again, why you need to re-architect your cost model to now take MVM in consideration. And at most, there was a 1% degradation in performance because of this. So again, the main takeaway from this is that we need to now reconsider how we do cost model estimations in our database system to now be mindful of the fact that MVM is byte addressable and the read-write speeds are much lower than in a disk-oriented model. So in the same way that 15 or 20 years ago, there was a lot of research done on cost models for main memory database systems, we suspect that going forward, we'll see a major trend in this area as well. All right, so now to finish up, I want to discuss sort of at a high level some of the lessons that we've learned at Carnegie Mellon in the process of building our own database system for non-volatile memory. And we touched a bunch of these different points as we went along during the tutorial, but I just want to sort of highlight them again. So the main takeaway from this entire tutorial is that MVM is so different than SSDs and DRAM that it really requires us to rethink and re-examine all the different design choices you have to make in your database system from the top to the bottom. And this is necessary in order for you to, for the database system to be able to release the full potential of the storage properties and performance properties of NVM that go beyond what DRAM and SSDs can actually do. And so as we showed at the very beginning, we sort of did a thought experiment where we said, well, what would the world look like in 10 years from now if DRAM and SSDs go away? What would the system look like if you only had NVM? And this allowed us to identify what were the key components in the system that we wanted to sort of target first in dealing with NVM and optimizing the system. And in our case, we saw that the logging scheme was the most important thing, and that's sort of what we tackled first. The other major thing, and the other major takeaway, is that NVM invalidates a lot of the sort of conventional wisdom that has been built up from the last 30 or 40 years in designing database systems to deal with fast volatile DRAM and slow non-volatile hard disks and SSDs. And again, when you teach an introduction database course to undergraduates, you spend all this time dealing with this dichotomy between these two different storage devices. But now with NVM, we think a lot of this is actually going to have to get thrown away, and we have to redesign our courses to now take this in consideration because the performance difference between reads and writes and DRAM and NVM is so much smaller than it is with an SSDs. And we also now take consideration as well the fact that reading and writing to memory locations in NVM are not going to have the same speed as you would in DRAM. So we have to redesign our algorithms to be mindful of this as well. So the overview, again, what we just went through this tutorial is that, again, we started at the bottom. We talked about how you would actually build an allocator that provides an interface to the database system process to non-volatile memory. We talked about what are the guarantees or the mechanisms that this allocator had to provide, right? So things like durability and naming, so that if your system crashes or that you lose power, you come back and all your pointers are still valid and all the data that you stored is still there. And then we built on top of that and constructed a storage manager that was able to reduce the amount of data you have to write out to NVM because we only need to store metadata rather than complete copies of that data. And then from there, we talked about how we had to deal with moving data between the different layers and how you build different data structures or indexes to use NVM correctly. And then I sort of finished up with a discussion of what has to change in your execution engine to now use NVM correctly once you have all these other components. So for future work, we talked a little bit about the data placement issue and access methods, which Wolfgang and Ismail will talk about in the next tutorial right after us. We also think there's a lot of work to be done in query optimization, not only at sort of the cost model level, but we're very interested in seeing how query compilation using LLVM or just-in-time compilation, how that is affected or what you need to change for that to using NVM. And then but I think we'll see the most of the effort in the non-volatile memory database research in the next couple of years will be focused on the storage layer, because that's where the most of the change is actually needed. And sort of some of the things we talked about here is just initial proposal. We think there's a lot of other ideas or other architectures you can try out with MVM once we get closer to the actual storage devices coming out. So to finish up, the bulk of the discussion for our work at CMU for non-volatile memory databases have been in the context of a new open source Apache licensed database system called Peloton that my students and I have been building at CMU for the last 2 years. So you sort of think of this in the same way that Postgres was the open source disk-based database system that came out of academia that everyone uses. We're actually spending the time and effort to have Peloton be the open source in-memory or MVM database system that comes out of academia that people use going forward. So we've designed the system from the onset to use MVM natively, and so that when the storage devices actually come out, we don't have to go back and make major changes to our system in order to use it. Whereas I suspect that all the open source systems, and certainly the commercial database vendors, will have to make major changes to use MVM in the way that we talked about here today. There's another aspect of the system where it's designed to be completely autonomous, using deep learning and reinforcement learning to have the system automatically tune itself over time. That discussion is not for here today, but we can talk about that offline as well. And since I know people from industry are here, again, I'll point out that this is 100% Apache licensed. No GPL, no closed source. All right, so with that, Joy and I would like to thank everyone for sitting with us today, and we'll be happy to answer any questions that you may have. Actually, stand up. Yes?
So Intel just released sort of consumer-grade NVMe cache drives that they call for 16 and 32 gig
Yes.
devices on the consumer market.
Yes.
Do you think they may benefit databases in some way without modification?
So his question is, Intel announced in March, under the brand name Optane, their new non-volatile memory storage devices. And they sort of have two versions of it. They have this cache thing, which is super cheap, and the idea is to sort of sit in front of an SSD. And then they have the actual Optane device, which is a NVMe SSD that sits on the PCI Express bus. I would argue that these are just faster, cheaper SSDs. They're not game changers at all. As I said in the beginning, it's the NVDIMP that actually, form factor that actually sits in the DIMM that is actually truly persistent memory. That's the thing that we've been focusing on here. That's the big game changer. Although I'm on camera, I don't want to say too much. The 2018 is when it's starting to smell like it's starting to come out. I'm actually going there in 2 weeks. They supposedly have something to show me, but we're getting very close. I'm very optimistic. Samsung, yes.
So seems that the only non-volatile memory devices are in the range of DRAM cost rather than NAND flash cost.
Mm-hmm.
I see that NAND is actually 10x cheaper than NVM today.
Mm-hmm.
And there are technologies like rack level battery backup, which can make your DRAM turn into a more resistant power failure safe device.
Mm-hmm.
So will NVM still be appealing to database development?
So,
The first question.
well, let me answer that first because that was a lot. Okay, so the fellow from Samsung here said that the current cost of NVM is 10x DRAM or flash, and that one could use like in the NVDIMM F form factor, where you have flash and DRAM with a battery backup, would that supplant NVM? Is that a better target for what people should be focusing on than sort of truly persistent memory like phase change and resistive RAM? I would say that if you can match the speed of what NVM can do, and it's in that sort of, it's byte addressable, then I actually don't care whether it's NAND flash or whether it's PCM or whatever. Like, we don't care, right? We'll use anything. So as long as you can provide those guarantees, and if the cost is cheaper, then yeah, yes, definitely, yes. from a research standpoint, again, if it's just block-based storage that's just a little bit faster, that's from, from a pedagogical standpoint, that's not that interesting. There's nothing really to learn from that. There's other, we can focus on other problems.
So, and then I thought that the PRAM, PCM-based memories are very power hungry.
Yes.
So if you really measure the power, the write throughput with the flash memory, you have to think about the power constraint, and you cannot get the maximum write throughput out of a PRAM-based either SSD or DIMM. You may need to consider actual constraint power as well.
Yeah, so his comment is that in the case of phase change memory, if you don't know what phase change memory is, the basic idea is that it's these little cells, and you basically run a charge to them, and you sort of heat them up, and they're like crystals. If you run a certain voltage at them, they become opaque, and that stores 1. If you run a lower voltage at them, they become clear, and that becomes 0. So sending that voltage in to modify its state actually consumes a lot of power and actually generates a lot of heat, which is another major consideration. And your statement is that with NAND flash, again, that they are less power hungry, and therefore you can have more of them stored in a sort of rack unit. Yes. I actually think that PCM is not interesting. I will fully admit that I drank the Memristor Kool-Aid. And again, although that's not out yet, and it's not clear what Intel actually has, whether it's PCM or resistive RAM, when you look at the power consumption for resistant RAM as prophesized by HP, it's much, much less. And that, I think, is the right technology. Now, going even farther forward, we can talk about spintronics and magnetic resistive RAM, which even has lower power consumption. So I absolutely agree. PCM is not ideal. If it's the new stuff is PCM, that might be a stopgap, and flash sticks around for a little bit longer. But I think there's other technologies coming out later, whether it's a decade or how much longer. I think that's more interesting. Another aspect that you actually didn't bring up either as well is when you start talking about 3D stacking of these non-volatile storage devices, and actually if you want to even put it on the actual CPU, you can't put PCM there because of that sending that voltage in. They heat up too much, and that adds heat to the CPU. Whereas spintronics thing, you could actually put on top of it. I'm not a hardware guy. This is just like from my conversations. This is my understanding of how this stuff works. Question, yes.
I have a short question regarding your experiments where all cache line are being written on the non-volatile memory. Now, you use the store instruction, right? And you mentioned that for these read-write asymmetry, where the read speed is going to be about 200 nanoseconds and the write speed is going to be in the upper nanosecond range, lower millisecond range. Now, what is going to be the effect of performance and manifold scalability on the one hand? And then on the other hand, what is going to be the effect of actually getting the advantages of those atomic instructions?
All right, so let me see. Your question is, if now the loads and stores are asymmetrical, what would the effect of that be on a multi-core database system architecture? And then what was the second part? Sorry.
Do you envisage a change in the atomic instructions so that we don't have to wait all that much before we move on, right?
All right. So again, I think your statement is what do you have to change if you want to consider a multi-core architecture when the read operations are now much faster than the write operations? That's a good question. I'd have to think about that. You have a question? You want to go for it? You have nothing?
No. So, are you talking about like locking? Because that is.
Yeah, are you talking about OTP or?
Yeah, like so your question was basically how does read-write asymmetry affect locking? I guess in some sense, right? You're talking about atomic instructions, right?
I'm actually talking about latching.
Yes.
And the key point of those atomic instructions is you avoid the latching. And because you don't have the latching, you can have the full scalability of the multi-cores.
Mm-hmm.
But now the game's changed. Now if I default store, then I have to wait in order to make sure that everything is written before I move on. Right?
So
So yeah, so now I understand what you're saying. Latching, you don't need to store that actually in MVM, right? Because latches don't persist after the database system stops, right?
unless you want a persistent lock table.
Because you want to make sure that whatever you stored is lands actually on NVM before you move on.
No, but that's not a latch. You wouldn't do that for a latch. Even then, a lock, you wouldn't necessarily do that because you'd crash and come back and wipe out the lock table. That doesn't matter. I'd have to think about, I think for other things, you would maybe want to do compare and swap on, like, in the versioning information in the tuple header.
I mean, you showed such an experiment, right, with the multi-versioning.
Yeah.
And this is where you need atomic swap and compare, which is going to bring you into exactly this scenario, wouldn't it?
Yeah.
So another minor comment is that with the deprecation of pcommit in the last few months, the programming model is much more simple in some sense because you now only have to reach the memory controller buffer. That simplifies things. To a first order approximation, it essentially hides the latency of the NVM device itself. Just a minor comment, yeah. But a very good question. Yeah.
Yeah, so I have to admit, we have not fully considered this because the emulator thing we have, everything's symmetrical. But let's talk about that offline, though. That's a good point. Yes? Over what, sorry? What's that last part? I'm missing. I can't.
So I am still trying to find what is the potential optimization you can achieve over a world without NVM. I hope I can just
Over with and without MVM, or
It's just with and without NVM. Like what is NVM actually?
oh, what is it? MVM. So
So at least 1 to 2 orders of magnitude improvement in performance, because once you bring in SSD into the picture, things are like at least 10 to 100 times slower. So in a world with NVM, for applications which care about durability, like database systems, it makes a world of difference. Yeah.
it seems like NVM basically brings a different set of trade-offs. So it did not seem very clearly, it was not obvious that it's going to improve your performance significantly over a memory database.
So even in a main memory database system, because you care about durability, you have to persist the data on a persistent device like an SSD or a hard disk. So compared to a world without NVM, performance of database systems would be much higher if NVM exists in the storage hierarchy. So that should hopefully answer your question. Doesn't matter if the database system is a main memory database system or a disk-only database system. Yeah.
I'll say also too, like I can't give you an exact number because, as in all things in databases, it depends on the application.
Yes.
Right? If you're just reading things once a minute, who cares? But if you're actually trying to write a lot, then it could matter a lot. And I also say too, there's other aspects of the system that affect performance. Concurrent control is a big deal, right? So I just can't give you like, oh yeah, it's always 10x, right? It depends on a lot of different other things. Question, yes.
So when you were talking about a query optimizer product, you mentioned experimental results using Postgres. Do you have even like partial results using a DBMS that's closer to the state-of-the-art with respect to analytic processing speed?
No, so I would say one again. That was work not done by us. Was it? What was it? Who was it? But
This was from one of the TU schools.
The work.
No, I think that this is a very interesting question, and there is actually a lot of scope for work to be done in this space. That's why we highlighted that problem. And this is like essentially a starting point of a line of research that has to be explored yet. And this particular work, they used Postgres because Postgres has a well-defined cost model and it's easy to tweak. Maybe it would be interesting to actually do similar experiments with other database systems, which are more like state-of-the-art, like, yeah, and see how things change. So that has to be explored.
not to plug our own system again, but we have an open source implementation of the Cascades optimizer. As far as I know, we're the only ones that have one. We have now we do now want to plug in a new cost model to take NVM into consideration. All right. Yes. So his question is, have we done any comparison with a column store database system on NVM? I believe at this point, all of our experiments have been on a row storage system. So now in Peloton, it actually is a hybrid system. You actually can take a table and store some of it as rows and some of it as columns. But for all the experiments we've done at this point, we've been focusing on OLTP because those are the write-heavy workloads. And so that you always want to store as a column store. The next phase of Joy's dissertation and our research is that we want to now look at analytical machine learning and AI workloads where you do want to store things as a column store. And that's actually ongoing research for us right now. And Joy will be finishing up and going on the job market a year from now, so you could hire him if you want to learn more. Yes, in the back. It's like the fans right there. Sorry, say it again. I think I heard your question is how does if you have a write behind log, how does that affect with replication? Because you normally could just replicate the write ahead log, but the write behind log has only metadata. Right. All right. So his question is how would you, if you have multiple machines, how would non-volatile memory work if your protocol is using write behind logging and you're only storing pointers and metadata for what you've modified on the master machine? How do you propagate those changes to the slaves or to the replicas? So in actually the write behind logging paper, we don't have graphs here. We actually show this. We actually got Intel to put a second NVM machine up for us in their lab, and we showed that write behind logging is perfectly compatible with a replication scenario. You essentially have to transform it from a write behind log into a write ahead log because there's no way to get around this. You have to copy the data to propagate it over to the other machine, right? So there's nothing about write behind logging that prevents you from doing that.
I would just like to add that with the newly proposed NVM over Fabric standard from Intel and a bunch of other companies, things might change because they know that network latency might be the high pole in the tent compared to storage latency. So with these new standards, you might want to come up with like remote memory access protocols to actually hide the network latency. So yeah, so this is again like a area where we need to do further work. Yeah. Thanks.
Yes.
So we have compared your recovery with traditional areas recovery, right? So we have log analysis we do, but did you compare that with like on-demand areas?
So his question is, in the case of write behind logging, we compared write ahead logging, which is always the canonical Aries implementation. Did we compare the sort of a newer version of Aries from Gertz Graphy on instant Aries, right? Instant recovery. Yes, we did. I think we did a comparison of that, right? We don't have graphs here.
Yeah, we don't have graphs. So at a higher level, I think write behind logging has a different asymptotic complexity compared to write ahead logging. Write ahead logging is O of n, it's linear with respect to the number of log records, and write behind logging is O of 1, it's constant. So that I think would be a more significant factor as opposed to the actual constants involved with the particular implementation of the logging protocol. Yeah, I hope that answers your question. Yeah, thanks.
Okay, it's 3:30. I think we're done, right? All right, we'll be around for the rest of the day. So in the same room right after this, Wolfgang and Ismail from TU Dresden will be presenting sort of more detail how to do non-volatile memory data structures. So if you're interested in this kind of stuff, you just stick around and see their talk next. Okay? All right, thanks.